Hi guys, so today I'll be explaining the chemistry final past papers. Now this is in the material for paper 2. Best paper 2 and paper 1 have the same material, like the same chapters and everything, so you're supposed to know this anyways. So do it if you want to. If you don't want to, just leave, it's fine. Okay, and here is the paper that I opened, in case you want to follow up while I'm solving it. And for this paper, we only need question number 1, 2, and 3. So let's start. Hot powdered lead oxide is reduced by methane, a flammable gas. The products are lead, steam, and carbon dioxide. Figure 1.1 shows the apparatus used to reduce lead oxide using methane. So let's explain the question, like in depth. Hot powdered lead oxide. So what needs to be heated? The lead oxide. It needs to be heat. Okay, is reduced by methane, a flammable gas. So what's flammable? Methane. So just arrow here. And the products are lead, Pb, steam, H2O as a gas, and carbon dioxide, which is CO2. Here's the figure. Let's try to label some of the apparatus. This is either a boiling tube or a test tube. Now they both look the same, but the main difference is that a boiling tube is used for heating, and a test tube, you can use it to just mix stuff or whatever. Just watch particles, watch chemicals react or whatever, okay? And a boiling tube is thicker. Now how do I know if this is either a boiling tube or a test tube? By reading the question. Here it says hot powdered lead oxide. So what's hot? What do you need to heat? The lead oxide. Okay? So this has to be a boiling tube. So there is that. Now this one can either be a boiling tube or test tube. This one, it doesn't matter because it's around ice. It's not gonna, like, nothing's gonna happen to it. And A is a beaker. Okay, so name the item of apparatus labeled A. We already said it's a beaker. Beaker. Draw an arrow on figure 1.1 to show where the apparatus should be heated. Now if we read the question again, hot powdered lead oxide. So what needs to be heated? The lead oxide. Where's the lead oxide? Over here. So where do we draw the arrow? Over here. Okay? Explain why powdered lead oxide is used and not a large lump of lead oxide. So why do they use powder instead of just like a large lump of lead oxide? Now think. What's the difference between powder and a large lump? Surface area, right? So you can say, let me explain more. So surface area. So why does surface area matter that much? Think of it this way. Let's say I have like some tea over here and I want to add some sugar. I can either add a sugar cube or grains of sugar. Which one's gonna melt faster? The grains of sugar. Why? Because of the larger surface area. Okay? So it's gonna react faster and the rate increases. Right? So back to this question. Why do we use powdered instead of a large lump? Because of the surface area. There's a greater surface area, so we can say the greater surface area, and we can say, you only need to say one of those because it's only one mark. So you can say greater surface area, or you can say reaction rate increases, or you can say react faster. Okay? You can say all of them is fine, but you're not gonna get any extra marks, just one mark. So you either say great surface area, reaction rate increases, or reacts faster. Okay? All of them are correct. Okay, D, explain what happens at point labeled B. Let's go back up. Here. What happens at point B? So we know that the lead oxide and the methane, when they react, its products are gonna go over here. So lead, steam, and carbon dioxide are gonna go over here. And then they're gonna get cooled. And then something's gonna happen. Now what changes? What can I say changes? Like you can say like something changes state. What changes state when you cool it? Water, like water vapor. So you can say that the water vapor or the steam gets cooled and then it condenses and turns into water. Because if you cool if you cool CO2, is it gonna change into, I don't know, like it's not gonna change, okay? And lead, it's gonna probably, carbon dioxide and lead, they're gonna escape from here. but the water is gonna go down here and condense and get cooled and then get condensed. Okay, so we can see down here the water, steam gets cooled and then condenses into water. So 1 mark here and 1 mark here, they need 2. Okay, so here if you see these 2, you're gonna get the full mark. The waste gases contain methane. State why the waste gases should not be released into the laboratory. Now go back to the question and read it again. Hot powdered lead oxide is reduced by methane, a flammable gas. We can stop here. Why should methane not be released into the laboratory? Because it is a flammable gas. So we can say because it is flammable. Flammable or flammable, whatever. So I say flammable. Question number 2. A student investigates how the rate of the reaction between aqueous nitrate and aqueous sodium thiosulfate changes with temperature. The student does 5 experiments using the apparatus shown. So their eyes, and they're gonna add sodium thiosulfate and a beaker of 100 centimeters cubed, 50 centimeters cubed of aqueous iron nitrate, a printed sheet and printed text. Now I'm gonna read this whole thing, but what you need to mainly know, and we're gonna read all of this and check the difference. You're gonna need to know that for later. Like check the main difference they're doing. مش صح. But they're gonna have to change one thing to check what happens. Like هلا you're gonna know. I'm gonna read that now. Okay, so one thing is gonna change and everything else is gonna be constant and not change. So experiment 1, use a 50 centimeters cubed measuring cylinder to pour 50 centimeters cubed of aqueous iron nitrate into a 100 centimeters beaker. Stand the beaker on printed sheet. Use a 100 centimeters cubed measuring cylinder to pour 5 centimeters cubed of sodium thiosulfate into the beaker, and at the same time start a stop clock. Use a thermometer to stir the contents of the beaker. Look down from above the beaker, and when the text on the printed sheet becomes visible, stop the stop clock. Use a thermometer to measure the temperature of the solution when the text becomes visible. Rinse the beaker and thermometer with water. Experiment 2. Use the 50 centimeters cubed measuring cylinder to pour 50 centimeters cubed of aqueous iron nitrate into the 100 centimeters cubed beaker. Heat the beaker on a gas over a Bunsen burner until the temperature of the iron nitrate has increased by about 5 degrees Celsius. Now look, here, this whole sentence wasn't up. Yani that's the thing they're changing. They're heating the iron nitrate, okay? So here in experiment 1 they didn't heat it. Here they heated it so till it increased by 5 degrees Celsius. So it increased by 5 degrees Celsius. And everything else is the same. So I'm not gonna bother reading. Experiment 3, same thing, and the temperature, they heated it until the temperature increased by about 10 degrees Celsius. Here, experiment 4, 15 degrees Celsius. Experiment 5, 25 degrees Celsius. Okay, so here we're gonna have to read the stop clock diagram. I'll show you how. So the circle that's outside is the seconds, they labeled it. Circle inside is the minutes. And we're just gonna start counting. The longer arrow is for the seconds, shorter arrow for minutes. So let's zoom in. Okay, so for seconds we're just gonna skip لغاية, let's say here, because it's closest to the arrow. I'm not gonna start counting like 1, 2, 3 لغاية 40 to 45. You don't need to. If they already started from like 45 here, like start from the number that's closest to the arrow. Like here, what's closest? 45. Because you don't need to count until you reach 45 if they already gave it to you from here. Okay, so 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56. So we have 56 seconds, and let's check how many minutes. 1, and just 1. You always go to the number smaller. Like here it's 1 point, maybe like 6, 1.8. No matter how close it is to the next one, you're still gonna take the number smaller. and even if it's like 1.9, you're gonna take 1. Okay? Unless there's like smaller lines. Here there's only like those like big lines, so it's only gonna be 1. Okay? Like if it was more specific and there were like smaller lines, let's say like till here, then okay, then yeah, then we count. But if there's no small lines, it's only like a wide gap, then you're just gonna take the smaller one. Okay? So let's just make it bigger again. So here it's only 1. Okay? So 56 seconds and 1 minute. So 1 minute. So 56 seconds and 60 seconds, because we're supposed to keep it in seconds. 56 plus 60, we get 116 seconds. Okay? And now let's see the thermometer. Here it's 20 and like a half. Okay, look, in the clock, in the stop clock diagrams, we're gonna make it more like, we're gonna round it. But here we're being more specific, okay? In temperature, we be more specific. So here it's like 20 and a half. So 20.5 degrees Celsius. Okay? Now let's scroll down. Here we have, let's start from here, 15 seconds, 15, 16, 17, 18, 19, 20, 20 seconds, and how many minutes? 1 minute. So, oh my god, 1 minute. So 60 plus 20 is 80. Now let's see the thermometer. 25, 26, 27, exactly 27. So 27.0 degrees Celsius. Here we start 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 seconds and 1 minute. So that's 60 plus 9, 69 seconds. Then here it's exactly 30 seconds, so 30.0 degrees, 30 minutes, 30 degrees Celsius, so 30 degrees Celsius. And then here it's, they start here, so 46 seconds and 0 minutes. So only 46 seconds. And then here 35, 36, 37, 37.0 degrees Celsius. Then last one, 15, 16, 17, 18, 19, 20, 21 seconds and 0 minutes. So 21 seconds. And then the temperature is 46.5. So 46.5 degrees Celsius. Okay? So these are all the answers. And now I have to plot it. I'm not gonna be that accurate, because if I'm gonna be that accurate, I'm gonna have to take me like 30 minutes. So I'm just gonna estimate, okay? So let's say the highest point has to be 116, because that was because the seconds are on the left. So 116, that was the highest. Okay, that was the highest amount of seconds they left it. So 116. Let's say under that we have 80. Let's say it's like here. And then under that we have 69, maybe here. And then 46. And then 21. Okay? So here 21, 46, maybe okay. And then 69, 80, and 116 here, okay? So at 21 seconds, how much was the temperature? 46.5. So 40, 1, 2, 3, 4, 5, 45, 46, and 46.5, so around here. So it's supposed to meet around here. Okay, and then at 46 seconds, how much was the temperature? 37. So 46, 31, 2, 3, 4, 5, 6, 7. This is 37. Then check. Okay, here. And then 69, where's that? Here, 69 seconds at 30 degrees Celsius, so 30 here and here. And then at 80 seconds it's 27 degrees Celsius, so 21, 2, 3, 4, 5, 6, 7. And then here, okay, wait. So around here. And then at 116 seconds it's 20.5 degrees Celsius, so 25 is here, and 25.5, so around here. And then, oh my god, so around here. Okay, and then we're supposed to draw the line of best fit, which you know what that is, hopefully. It's like a line that passes through all the points, pretty much like this. And then, okay, that's pretty much how it's supposed to be like. Deduce the experiment in which the rate is fastest. So here they only give us a temperature, and we know the higher the temperature, the faster the rate. So the temperature with the highest temperature, experiment with the highest temperature, so experiment 5, because here it's 46.5 degrees Celsius. So experiment, I only write 5. Okay. Use your graph to predict the temperature of the solution when the text becomes visible after 55 seconds. Wait, it's not that accurate. So let's say like 56, 57, 58, 59, 60, 60. Wait, what? No. 46, 47, 48, 49, 50, 51, 52, 53, 54, 55. Yeah, no, I should have made it more accurate. Okay, let's just estimate. If this is 46, then 55 is supposed to be around, let's say here. So the temperature would be 31 to 32.5. This is not accurate at all, by the way, so please, in the exam, please make it accurate, don't estimate. Okay, and then down, explain why wrapping the beaker in cotton wool after it has been heated will improve the accuracy of the results obtained. So after we heat something, we have to like cover it to insulate it, to like keep it warm, right? No, the answer is you have to insulate it, like you have to cover it to keep it. Okay, but like let's say it's my like okay, this is the beaker, and they cover it in wool. Let's say this is the wool. Oh wait, let me use a different color, highlight it. Okay, let's say this is my wool. Okay, how will this improve my accuracy after heating it? Like obviously I heated it first and then I added the cotton. We know initially insulated will keep the thing warm and the temperature becomes constant. It like stays the same for a longer time. Okay, so the answer, it's 2 points, 2 marks, so we're just gonna write 2 stuff. So we can say it reduces the heat lost, the amount of heat lost, and makes the temperature constant, or like more constant. Okay, now explain why it would be an improvement to measure the volume of aqueous iron nitrate in a burette rather than a measuring cylinder. We know that a burette is way more accurate than a measuring cylinder. A burette, it's like this, kind of, and then a measuring cylinder is like this. Then there's like the lines, and then here it's like the lines. Okay, this is way more accurate rather than this, so we can say it's more accurate. Now that's the only thing you need to say. It's also only 1 mark, so more accurate. Suggest why it would not be an improvement to add the aqueous sodium thiosulfate using a pipe. Okay, so this is the burette. My handwriting is amazing. And this is the pipette. And if you remember from last year, the pipette, you have to like put like something red over here, and then you keep like squeezing it until it reaches the mark. Okay, so like it takes longer. It is slower than a burette, but it's more accurate. But we don't need that for a reaction. Why? Because it directly reacts when you put the thing, when you put the sulfate, whatever it is, when you put them together, they directly react. But we don't do like that won't work properly if we keep adding it slowly. We're gonna need to add it faster using what? A burette. Okay, so that's why it's better to use a burette rather than a pipette. Burette is not that accurate, but it's faster, and a pipette is way more accurate, but it's slower. Okay, so it's better to use a burette because it's faster and it's a bit more accurate than a measuring cylinder. And it's not better to use a pipette. Why? Because it is slower but more accurate, but it won't make that much of a difference if it's gonna start the reaction quicker and like not make the reaction proper. Okay, because it is slow where to add. Okay, and then here suggests why the aqueous sodium thiosulfate must be added after the aqueous iron nitrate has been heated and not before it has been heated. Okay, so why should we heat it before adding the iron nitrate? So why should we heat the sodium thiosulfate before adding the iron nitrate? Okay, so let's say this is my what's it called, iron nitrate, and I'm supposed to heat it. They're increasing the temperature in each experiment, and then add the sodium whatever. Why should I heat it first and then add the sodium? Because if I add the sodium first and then heat it, it would have already started reacting, right? But that's why we have to heat it first and then put the sodium whatever. Okay? So why? Because it will react while heating. Okay? Describe how the results of the experiment would change when the experiment is repeated using a 250 centimeters cubed beaker in place of the 100 centimeters cubed beaker. So they're saying, and originally they were using a 100 centimeters cubed beaker, right? So let's say this is the 100 centimeters cubed beaker, and this is the 250. Let me make it longer. 250 centimeters cubed beaker. So what were they adding? They were adding the iron nitrate, 50 centimeters cubed of iron nitrate, and 5 centimeters cubed of the sodium thiosulfate. So it would fill up around half of the 100 centimeters cubed beaker. But in the 250 centimeters cubed beaker, it would fill up maybe like a quarter. So it would fill up like less depth. So what's the main difference between these two? The depth, right? Here it is deeper rather than here. Here it's more shallow. So of course, since here in the 100 centimeters cubed beaker it is deeper, it's going to take more time to react and show the text that they're trying to see under the beaker. But here, since it's shallower, it's going to take less time to show the text that they're trying to see under the beaker. Okay, so what's the answer? The change in results would be it would take less time. And why? Explanation: because there is less depth of the liquid to look through. Okay, so here it's 2 marks. 1 mark for this and another mark for all of this. Okay? 3. A student tests 2 substances, solution F and G. Tests on solution F. Okay, so he did the flame test and then he got a light green color. We know that a light green color comes from Ba2+. Test 2. The second portion of solution F, add 1 centimeters depth of aqueous sodium hydroxide, so NaOH, and a piece of aluminum foil. So they added aluminum foil. Warm the mixture and test for any gas produced. Effervescence was seen, يعني a release of gas, and the gas turned red litmus paper blue. Now, you know that whenever they add NaOH, let's say this is a substance, plus NaOH and aluminum powder, aluminum foil, which is the catalyst, and then you heat it, you would get NH3, which is the thing that turns the gas that turns red litmus paper blue. So how do I know if it's either NH4 or NO3? Because we know whenever we add NH4 and NaOH and we heat it, we get NH3. And also when we add NO3 to NaOH and we heat it with aluminum powder, we get NH3. The main difference is that only with NO3 to minus we add aluminum powder. Only with NO3 to minus. Okay? So this one has to be NO3 to minus, because they added aluminum foil. Okay? And then to the third portion of solution F, add the 1 centimeter depth of nitric acid, followed by a few drops of sulfur nitrate, so AgNO3. Okay, so they added AgNO3 and they didn't get any change. So we know the answer has to be also Ba. So BaNO3, because we already got it from the tests and observations. Okay, so describe how to do the flame test used in test 1. So if we want to do a flame test, what do? First we get a clean platinum wire, and then we dip it into the solution we are testing, and then we put it on top. So put on the blue flame of a Bunsen burner. Okay, you have to say blue flame. Identify the gas given off in test 2. It is NH3. Remember here we said NH3. And then identify solution F, Ba2 plus, NO3 2 minus. You can say that, or you can say BaNO3. Oh wait, it's NO3 minus, not 2 minus, sorry. So it's gonna be BaNO3 2. Because when you cross multiply, they're not gonna cancel. When you do Ba2 plus and NO3 minus, when you cross multiply, you're gonna get BaNO3 and brackets 2. State what would be observed if the student adds sulfuric acid, so H2SO4, to another portion of solution F. So what in BaNO3 reacts with H2 or SO4? We know that Ba and SO4 react to give a white precipitate. So that's the answer. Okay? Now tests on solid G. Solid G is iron carbonate, so FeCO3. About 10 centimeters cubed of dilute sulfuric acid, so H2SO4, is added to solid G. Any gas given off is tested. So H2SO4 is an acid, so any of these two react with an acid. Do any of them react with an acid? Yeah, CO3 to 1, CO3. We know that when CO3 reacts with an acid, it releases CO2, colorless. Gas turns lime water milky. Okay, so you can say it releases a colorless gas or bubbles of gas that turns lime water milky. And because it's 2 marks, you have to say lime water milky and colorless gas or bubbles of gas. Okay? To the product of E, so Fe2 plus. So Fe2 plus and CO3 2 minus. So which one of these reacts with NaOH? Fe2 plus, right? So when Fe2 plus reacts with NaOH, we get a green precipitate. So adding dropwise, we get a green precipitate. And if we add excess, it doesn't dissolve in excess. So still, you can see, doesn't dissolve in excess. Okay? And that's the end for this paper. Let me open the next. Okay, so this is the next paper. And if you want to follow up with me, this is what you need to search. And wait, let me. Okay, so for this paper, we need question number 3 and 4 from A to E and G. Okay, so question number 3. Over 200 million tons of sulfuric acid, H2SO4, are manufactured every year. State the name of the process used to manufacture sulfuric acid. It is the contact process. Okay. Part of the manufacture of sulfuric acid involves converting sulfur dioxide to sulfur trioxide, so SO2 plus O2 to give SO3. Describe 2 methods which sulfur dioxide, SO2, is obtained. So we know when we burn sulfur in the air, which contains O2 and N2, we get SO2, because the S and O give SO2. So that's one answer. We say burning sulfur in air. And another method is roasting sulfur ores in air. So sulfur ores, like ZNS, when you roast them with oxygen, you get ZNO and SO2. Okay, so that's another way to get SO2. So the first method is burning sulfur in air, and the second method is roasting sulfur ores in air. The conversion of sulfur dioxide to sulfur trioxide is a reversible reaction which can reach equilibrium. What are 2 features of equilibrium? Okay, so we know in equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction, and the concentration of reactants and products are constant, not equal, constant. And don't write like this unless you want a 0, yeah? Just like write the full sentence, please. So like the rate of the forward reaction is equal to the rate of the backward reaction, and the concentration of reactants and products are constant. Okay? State the typical conditions and name the catalyst used in the conversion of sulfur dioxide to sulfur trioxide. We know that the temperature is always in contact on Haber process for 150 degrees Celsius, and the pressure is 200 kilopascals or 2 atm, and the catalyst is vanadium pentoxide, or you can say V2O5. Okay, then here complete the table. 3.1 forward reaction is exothermic. So here exo, then backward is endo. Okay, and here they want to know what happens when you decrease the temperature. Okay, if my impulse change here for the first one is decreasing the temperature, equilibrium would increase the temperature by going to the exothermic side. So since the forward reaction is exothermic, so it's gonna go to the right, which would increase the amount of SO3. So amount of SO3 would increase. Now here for the second one, what would happen if my impulse change was to increase the pressure? Equilibrium would decrease the pressure and go to the side with the least amount of gaseous moles. Okay? So don't get confused when there's solid or aqueous or whatever, okay? Only gaseous, only count the gaseous. And moles are in coefficient. So here we have 2 and 1. Here we have 2. So in total, here we have 3. And here we have 2. if you want to go to the least amount of gas use moles, we're going to go to the smaller side, which is to the right. So the effect on the concentration of SO3 would be increasing. And if they added no catalyst, wait, I forgot to write here. Obviously, when you increase the temperature, increase the pressure, the reaction rate increases. Okay? And then here for the last one, no catalyst, the reaction rate would decrease and no effect. Both the addition and removal of a catalyst or an inert gas does not affect the concentration of any of the reactants or products, okay? Explain in terms of collision theory why reducing the temperature decreases the rate of the forward reaction. So whenever we see temperature, we're always going to talk about three stuff. First, kinetic energy, and then collisions, and then the rate. Okay? So when we decrease the temperature, what's going to happen? There's going to be a decrease in kinetic energy of the particles, which would decrease the amount of collisions, I don't know how to spell it, collisions between particles, which would decrease the reaction rate. Okay, so you have 3 marks, 1, 2, and 3. Okay. Sulfuric acid contains SO42- ions. The oxidation number of O atoms in SO4 ions is what? Wait, is this coming? A to E, A, B, C, D. Wait. Okay, I checked how to solve this. It's pretty easy. So what you're gonna do is 4 times this up here, which is -2, which would be -8. So then you're gonna do -8. Wait, again, let's try it again. Okay, so 4 times -2 to be -8, and then you're gonna add that to S, and that would be equal to 2 minus 2. Okay, -2. Okay, so again, you're gonna multiply the number down, number up. I put it in brackets, then add that to what you're gonna find and make it equal to the oxidation number of O atoms. Okay, so when you solve, you're gonna get the answer to be 6, and just put a plus because there's a plus in the marking scheme. Okay, wait, there's 2 marks, so 1 mark for this and 1 mark for writing 4 times -2 separately. I don't know why. Okay. Question number 4. So solid sodium hydroxide, so NaOH as a solid, is a base which dissolves to form an aqueous solution, NaOH. State what is meant by the term base. We know that a base is a proton acceptor. Okay, I'll just write the answer first. Proton acceptor. What does that mean? يعني we know a base is like, for example, NH3, for example, and then if I add an acid to it, which H+, okay, it would take the proton. Okay, so it's a proton acceptor, just takes the protons. Okay, state the term given to a base which dissolves to form an aqueous. You have to memorize this, okay? The term given to a base which dissolves to form an aqueous solution is alkali. Okay? And here state the color of thymophthalate in NaOH. We know NaOH is a base, and thymophthalate in a base is blue. Or whatever. Okay, there's a table you need to memorize. Let me just write it really quickly. Okay, so litmus in acids are red, neutral purple, base blue. Thymophthalate, which is what we were talking about right now, is colorless in acids, colorless in neutral, and blue in base. Methyl orange is red in acids, orange in neutral, yellow in base. and phenolphthalein is colorless in an acid, colorless in neutral, but pink in base. Okay, so let's solve this. Wait, not this one. Okay, complete the word equation of the reaction of NaOH with ammonium chloride, so NH4Cl. So NaOH plus NH4Cl. Okay, so we're gonna get NaCl, so say NaCl, we'll outright the word, so sodium chloride, and the NH4 will become NH3 and H plus, so here ammonia, then that will go, and these two will go, these and these and these, so we're left with OH and H plus, and OH plus H plus, OH minus and H plus gives us water, H2O, water. Okay, state the term given to metal oxides which react with bases such as NaOH. So here it's gonna be amphoteric oxides. Okay, it's amphoteric because we know amphoteric reacts with acids and bases, right? So that's why it's amphoteric. Okay, and then name a metal oxide which reacts with NaOH. Just think of any amphoteric oxide, ZnO. Okay, F, we don't need it, F, and then G, it's not in the material, yeah? Okay, and then G, in titration, 25 centimeters cubed of 0.08 moles, okay, wait, so this is the volume, this is the moles per decimeter cubed, so the concentration, and then, wait, so that's the concentration of KOH, because potassium hydroxide, wait, let me write it down, KOH, and then it's neutralized by V2 of H2SO4. Okay, now here they want you to calculate the concentration of H2SO4 in grams per decimeter cubed using the following steps. Okay, so here they want you to calculate the number of moles of KOH used. We're gonna use the pyramid NCV. Okay, so N is the moles, V is the volume in decimeters cubed, and then C is the concentration. Okay, here we need to find the concentration of KOH, so 0.08 moles per decimeters cubed times, no, I don't need to write the, okay, so 0.08 times 25 centimeters cubed. Can we keep it in centimeters cubed, or do we have to turn it into decimeters cubed? We have to turn it into decimeters cubed. So divide by 1000, and then you're gonna get 2 times 10 to the power of negative 3, or you can say 0.002. Okay, yeah, that's it. Okay, so determine the number of moles of H2SO4 which react with KOH. So this stoichiometry, however you say it, whatever. So question mark, number of moles of H2SO4 react with KOH, which was 2 times 10 to the power of negative 3 moles. Then under that we're gonna write the moles of the coefficient, the coefficient of the substance in the chemical reaction. So H2SO4 here it's 1, so 1, and KOH here it's 2. So cross multiply, you're gonna get 1 times 10 to the power of negative 3, or again 0.001. Okay, I want you to calculate the concentration of H2SO4 in moles per decimeters cubed. So what do? First you're gonna find the moles of H2SO4, which we already found in the other question, so 1 times 10 to the power of negative 3 and divided by decimeters cubed. Now why? Because you can just copy what's here, so N divided by V, or you can just follow the formula, same thing. Okay, so to find the concentration we're going to do N over V, copying the pyramid, or you can just copy what's here. How much is the volume of H2SO4? It's 20 centimeters cubed. 20 centimeters cubed. Now can we keep it in centimeters cubed? No, we have to divide by 1000. So 1, 2, 3. Then you're gonna get 0.05 or 5 times 10 to the power of negative 2. Last question, calculate the concentration of H2SO4 in grams per decimeters cubed. Now how do you do that? First you're gonna find the mass of H2SO4. How do you do that? You're gonna do moles times molar mass. You know that the molar mass is 98 and the moles here it's 0.05. So then you're gonna get 4.9. Or you can do some other long way, which is finding the mass in kilograms in grams first. Yeah, grams. Okay, so moles times molar mass, you're gonna use the first moles, which is over here. 1 times 10 to the power of negative 3 times 98. You're gonna get 0.098 grams, and then divided by the volume to 20 over 1000. So you're gonna get 0.098 over 20 over 0.098 over 20 divided by 1123. So then you're gonna get 4.9. Okay, same answer, different ways. And that's it for this. This is the paper that I opened, and for this paper we need questions 1 to 4. And yeah, that's it. Okay, so sodium hydrogen carbonate decomposes when heated. The products are solid sodium carbonate, so NaCO3, water, H2O, and carbon dioxide. A student decomposes a sample of sodium hydrogen carbonate using the apparatus shown. So let's try to label the apparatus. A is either, again, a boiling tube or a test tube. And since they're heating the sodium hydrogen carbonate, it's a boiling tube. And B is a measuring cylinder. And if you can't see, like, it's a measuring cylinder, look, a measuring cylinder is like this. But they just flipped it so that the delivery tube goes through it and brings all the products over here. Okay? So A is a boiling tube and B is a measuring cylinder. When the sodium hydrogen carbonate was heated, a colorless liquid collected at the points marked X. So which of the products here are a colorless liquid? H2O, right? Water. So water. On the diagram, draw one arrow to show where the apparatus should be heated during the experiment. So again, read the question. Sodium hydrogen carbonate decomposes when heated. A student decomposed a sample of sodium hydrogen carbonate. So where should it be heated? Where is the sodium hydrogen carbonate? Over here. So the arrow should be here. State an observation that would indicate the sodium hydrogen carbonate had stopped reacting. Let's see here. Sodium hydrogen carbonate. So again, the products are sodium carbonate, solid sodium carbonate, water, and carbon dioxide. And these bubbles are CO2 because the water is here and sodium carbonate will just stay down because it's solid. So, of course, when all the sodium hydrogen carbonate decomposed, there would be no more bubbles forming, right? Or like the volume of the gas stops changing. So we're gonna say, well, it's only 1 mark, so we can say when no more bubbles form. Explain why it's important to remove the delivery tube from the water as soon as heating stopped. Okay, so let's go back up and try to think why. So here, they're gonna keep heating the sodium hydrogen carbonate until it stops decomposing. And when it stops decomposing, they stop heating it. So we know when it decomposes, it releases its products here, and then they go here. So if they stop heating it, which is when it stops decomposing, they have to directly remove the delivery tube. Why? So that the water doesn't go back in. Now there are multiple answers. Like I'll tell you, in the marking scheme it says so that the boiling tube doesn't break, and so that the water doesn't go back into the tube. So since it's 2 marks, we're gonna say 2 of those. So we can say the test tube or the boiling tube cracks and water goes into the tube. Question number 2. A student investigated the reaction between 2 different solutions of aqueous sodium carbonate, solution K and solution L, a dilute hydrochloric acid using 2 different indicators. The experiments were done. A burette was rinsed with water and then with dilute hydrochloric acid. The burette was filled with dilute hydrochloric acid. Some of the dilute hydrochloric acid was run out of the burette, so the level of the dilute hydrochloric acid was on the burette scale. Using a measuring cylinder, 25 centiliters cubed of solution K was poured into a conical flask. 5 drops of methyl orange indicator and 5 drops of beam of toluene indicator were added to the flask. The conical flask was placed on a white tile. Dilute hydrochloric acid was added slowly from the burette to the conical flask, while the flask was swirled until the solution turned yellow. This is the first color change. More hydrochloric acid from the burette was added to the conical flask while swirling the flask until the solution changed color again. This was the second color change. Okay, so here we're gonna have to read the burettes. So burette reading at first color change, here it's exactly 12, so 12.0, and then burette reading at second color change over here, it's first we're gonna count the number of gaps between 2 consecutive numbers. So look, we're gonna do number 2 minus number 1 minus number 2 divided by number of gaps. So number 1, 22, minus number 2, 23, divided by the number of gaps. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it's gonna be negative 0.1. That is the number. That's how much you add to each line. So this line is 23 minus here. This line is 23 minus 0.1. Okay. So 1, 2, 3, 4, 5, 6. 6 times negative 0.1, it's negative 0.6. We're gonna add that to 23. So 23 minus 0.6 is gonna be 22.4. So that's the number, 22.4. And that initial burette reading here, again we're gonna do number 1 minus number 2, 1 minus 2 over divided by the number of gaps. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each line is negative 0.1. And here we have 1, 2, 3, 4. 4 times negative 0.1. It's gonna be negative 0.4. Then you add that to 2. So 2 minus 0.4. It's gonna be negative not negative. You're gonna get 1.6. 1.6. Okay, now let me erase all that. Okay, volume of dilute hydrochloric acid added for first color change. So over here, you're gonna do the burette reading at first color change minus the initial burette reading. So you're gonna do 12 minus 1.6. Then you're gonna get 10.4. And then here, total volume of hydrochloric acid added for second color change. So second color change minus initial burette reading. So 22.4 minus 1.6, you're gonna get 20.8, and those are the answers. And we're gonna do the same thing for experiment 2. Burette reading at first color change over here. So 1, 2, 3. 20 minus 0.3, it's gonna be 19.7. And then final Burette reading at second color change over here. So 1, 2, 3, 4, 5, 6, 7. 7 times, no, it's negative 0.7. So 36 minus 0.7, 35.3. Initial Burette reading over here, it's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5 minus 0.9, it's gonna be 4.1. And then for the volume of dilute hydrochloric acid added for first color change, so we're gonna do the Burette reading at first color change minus the initial Burette reading. So 19.7 minus 4.1, the answer is 15.6. And then we're gonna do total volume of hydrochloric acid added for second color change. So the reading at second color change minus the initial Burette reading. So 35.3 minus 4.1, so then the answer is 31.2. State the color change observed at the end point when dilute hydrochloric acid HCl is added to methyl orange in an alkali solution. So we know alkali base, so here we had, let's say this is our alkali solution, the base, and then we added the dilute hydrochloric acid, and in the base we have methyl orange. Now if you remember the table I wrote, I don't know which past paper, but I wrote a table. Methyl orange in bases is yellow, but in acids they change to red. So again red, but since acid plus base gives us neutral, we have to say from base to neutral. So what's the color at the base? At the base it's yellow, and at neutral methyl orange is orange. So again I'm gonna explain it. We have the beaker that has a base and methyl orange, which tests the presence of acids and bases and whatever. So in acids, methyl orange is red. In bases, methyl orange is orange. No, methyl orange is yellow. And in neutral, methyl orange is orange. Okay? So if I have the base over here and I added my HCl, which is the acid, we're gonna get a neutral solution, right? Because acid plus base gives us a neutral solution. So this neutral solution will be detected by the methyl orange, and then methyl orange will turn to orange. So it was base, so yellow, because methyl orange was in a base before we added the HCl. So it was yellow here, base yellow, and then it turned to orange. Why? Because we added acid and base, and then we got a neutral solution, and in neutral solutions methyl orange is orange. So it went from yellow to orange. For experiment 1, compare the volume of dilute hydrochloric acid needed for the first color change with the volume of the dilute hydrochloric acid for the second color change. So let's go back to experiment number 1 here. So this is the first color change, and this is the second color change. So these two, it's almost double, right? So the volume doubled. We can either say it is double. Oh no, we have to say double and a greater volume is required to reach the second point. Let me explain why. Because look, first it was 12 and then it became 22.4. They added like more. So from this to that, it's almost double, right? And because it's double, we're gonna need a greater volume to reach the second point, which is here, right? Okay, here compare the concentration of solution K using experiment 1 to concentration of solution L using experiment 2. Since it's 3 marks, we're gonna have to say 3 stuff. So let's go back to experiment. We thought that they want experiment 1 to experiment 2. So this is experiment 1 and this is experiment 2. So look at what we're gonna do. So we're gonna add these 2 volumes of hydrochloric acid. We're gonna get for this 46.8, and for the first one we're gonna get 31.2. Now what's the relation between 31.2 and 46.8? 46.8. If we multiply by 1.5, we're gonna get that. So obviously, which one's more concentrated? The one with the higher volume of hydrochloric acid. So solution L is more concentrated than solution K. So let's write that. Solution L is more concentrated than solution K. Now how do we find that? Because solution K, solution L, has a higher volume of HCl compared to solution K. So solution L is 1.5 times the concentration of solution K. Okay, so this is 1 mark, this is another mark, and this is the 3rd mark. So we got the 3 marks. Now let me explain again. First thing we're gonna do is add the volumes of hydrochloric acid that we got here. So these 2. We're gonna get, for the second experiment, we're gonna get 46.8. And for the first experiment, when you add these 2, we're gonna get 31.2. And then if we compare these 2, we can see that the second experiment has a higher concentration of HCl compared to experiment 1. Experiment 2 is equal to, which is solution, I think, L. Solution L is equal to 31.2, which is solution K, times 1.5. So solution L is 1.5 times greater than solution K. So which one's more concentrated? Solution L. Okay? So solution L is more concentrated than solution K because solution L has a higher volume of HCl compared to solution K. Solution L is 1.5 times the concentration of solution K. Okay. Deduce the volume of dilute hydrochloric acid needed for the second color change when experiment 2 is repeated using 50 centimeters cubed of solution L. So let's go to experiment 2 here. 25 centimeters cubed. It's originally 25 centimeters cubed, so they doubled the volume. So what are we gonna do to the volume of the second color change? We're gonna double it. So 31.2 times 2. We're gonna get 62.4. So 31.2 times 2, 62.4. And then don't forget the unit centimeters cubed. 1 mark for the number and 1 mark for the unit. State why using 50 centimeters cubed of solution L would cause a problem. So we know in burettes they go from like 5 centimeters to 25 centimeters to 15 centimeters till the highest thing they can go to is 50 centimeters. So how can it hold up the 62.4 centimeters cubed of hydrochloric acid? It can't, right? So we're gonna have to say the volume is too large, or more than what can fit the burette. So the volume is more than what can fit the burette. State the advantage of using a pipette instead of a measuring cylinder in these experiments. We know that a pipette is way more accurate than a measuring cylinder. Look, a pipette, it's like this, and a measuring cylinder is just like that, with lines. So a pipette is more accurate, so all you need to say is more accurate. Explain why the conical flask was swirled as the dilute hydrochloric acid was added from the burette. So this is the conical flask, and let's say this is our hydrochloric acid as it's getting added. So why would they must mix it with a glass rod, for example? Just to mix it, that's what you need to say. To mix the solution. Okay, that's all you need to say. At the start of experiment 1, wait, what? Okay. At the start of experiment 1, the burette was rinsed with water and then with dilute hydrochloric acid. At the start of experiment 2, the conical flask was rinsed with water but not with solution L. Explain why the conical flask was rinsed with water. So again, here we have our conical flask and the burette. It says my burette. Okay? So the burette was rinsed with water and hydrochloric acid. But the conical flask was only rinsed with water, not hydrochloric acid. Why? Because they want to clean the residues from solution 1. They're using different concentrations of HCl. So why would they clean it with HCl? Because that would add more volume of HCl to the conical flask. Like maybe it would be stuck as residue or whatever. Okay? So we're just gonna say to clean the residues from experiment 1. Explain why the conical flask was not rinsed with solution L in experiment 2. Again, I already said that, because if you mix it with the solution L, it's gonna add more volume or more concentration of the solution L, which would like affect the test which we're making, right? Now we're testing the color change of methyl orange with the change of volume of hydrochloric acid. So if I add more hydrochloric acid from solution L, it's gonna change our test and make it inaccurate. Okay? So the answer is it would add an unknown volume of solution L. Question number 3. Solid M and solid N are analyzed. Solid M is not iron nitrate, NO3, I think. Yeah, NO3 minus. So when you cross multiply, you get FeNO3 3. Solid M was dissolved in water to form solution M. Solution M was divided into two approximately equal portions in 2 test tubes. The first portion of solution M, aqueous sodium hydroxide, so NaOH, was added gradually until in excess. The product was kept for B. So when we add excess of NaOH to Fe3 plus and NO3 minus, which one of these will react or make a precipitate or whatever? We know that when Fe3 plus is added to NaOH, we get a reddish brown precipitate, right? So red brown precipitate. And then they kept adding until it was in excess. Does it dissolve in excess? No. So does not dissolve in excess. The product from A was transferred to a boiling tube. A piece of metal foil was added and the mixture was warmed gently. Any gas produced was tested. So, they added Fe3 plus and NO3 minus and there's still some NaOH left from the other experiment from part A, because they're using the product they said the product was kept for B. So Fe3 plus and NO3 minus and NaOH and aluminium foil, so Al, all of that, and they also heated it. So which one of these react with NaOH and aluminium to make a product? NO3 minus, right? So NO3 minus and NaOH and aluminium powder, which is the catalyst, when you heat them you get NH3, and then when you test it, because you said any gas produced was tested, turns red litmus paper blue. And then identify the gas made in NH3. To the second portion of solution M, about 1 centimeters depth of dilute nitric acid followed by a few drops of aqueous barium nitrate, so BaNO3 were added. So BaNO3 and acid and FeNO3, because they said solution M here, FeNO3. Do any of these react with an acid? No. So no change. Tests on solid N. Test 1. A flame test was carried out on solid N. The flame became red. Look, when they say red and not brick red, just red alone, then it is lithium. If they say brick red, then it's Ca. But it's lithium here because they only said red. So red is Li plus, and then they added dilute nitric acid. So acid and AgNO3, AgNO3, and there was no visible change. So it can't be Cl or Br or I, because I turns yellow when it's with AgNO3 and bromide turns creamy and Cl turns white, like the precipitates. I is yellow, Br is creamy precipitate, and Cl is white precipitate. In test 3 they added HCl, and then they got an acidified aqueous potassium manganese that changed from purple to colorless. So there's only one thing that does this. It's SO2. Okay, and how do we get SO2 when we add an acid? From SO3 to minus. So SO3 to minus and acid release SO2, which is a choking smelling gas that decolorises KMNO4 from purple to colorless. Okay, so the gas produced is SO2, and solid N is Li plus and SO3 2 minus, and then when you cross multiply we get LiSO3 2. Oh no, wait, no, it's Li2SO3. Next question. The diagram shows some coffee beans. Caffeine occurs naturally in coffee beans. Caffeine is a white crystalline solid. It is very soluble in hot water but less soluble in cold water. Plan investigation to obtain a pure crystalline sample of caffeine from coffee beans. Assume that all other soluble substances in coffee are very soluble in both hot and cold water. You are provided with coffee beans and common laboratory apparatus. 6 marks. So you have coffee beans. Let's say these are my coffee beans. First thing you're gonna do is just crush them into powder using a pestle and mortar. If you remember from grade 9, you know the pestle, the thing that's, and you crush them, okay, with a pestle and mortar, yeah. Okay, so when you So, okay, let me write the steps. First thing you're gonna do is crush the coffee beans with a mortar and pestle. And then, since they said that it's very soluble in hot water, or just water, let's just add water. Second thing, we're gonna add water to the powdered coffee and mix. Why? Because we're gonna filter it. Okay, so then now we're gonna third thing we're gonna do is heat the solution of water and powdered coffee for the caffeine to dissolve. Because remember, again, the caffeine is soluble in hot water, so we're gonna make it dissolve in the water and then filter it using filtration, and then we're gonna crystallize the filtrate that's left on the bottom. Okay, so step number 4 is filter the solution. Step number 5 is to obtain the filtrate which would be down, like let's say there's my conical flask and I have my filter paper like that. The coffee powder would be here, and then the caffeine and the water would be here. So we're gonna take this filtrate and crystallize it so we can get crystals of caffeine. Okay, so we're gonna take the filtrate. So first we're gonna leave the filtrate to form crystals and then rinse them. Okay, so that there won't be any like water or anything that's left on the crystals that would make it impure, because they want it to be pure crystalline. Okay, so again, first step, you're gonna crush the coffee beans with the mortar and pestle, and then you're gonna add water and mix the powder that you obtained with the mortar with pestle, and then you're gonna heat it since caffeine is very soluble in hot water, and then you're gonna filter this solution and then take the filtrate and do crystallization with it. And then when you get the crystals, wash the crystals so that they can become pure, because they want pure crystalline. And that's it for this paper. The paper I opened is here, and for this paper we only need question number 2. Calcium hydroxide CaOH is slightly soluble in water. Calcium hydroxide can be made by the reaction of calcium with water. Write the chemical equation for this reaction. Now if you're confused, just write what they give you. They told you H2O, which is water, and Ca to give CaOH2. So what's left? We already used, H2O is H plus and OH minus. We used the Ca here, we used the OH here, but we didn't use the H plus. So plus H plus, H2, okay? And then we just balance it, we put a 2 here, and that's it. Okay, so the answer is this. And please don't forget to balance it, because you get a mark for that. Name another substance that reacts with water to form calcium hydroxide. Okay, so CaO, that's the answer. Calcium oxide. Now how? Because calcium oxide and H2O, when they react, they release CaOH2. Okay? When calcium hydroxide, CaOH, dissolves in water, it dissociates its ions and forms a weakly alkaline solution. suggests the pH of aqueous calcium hydroxide. So we know any number less than 7 is acidic, any number greater than 7 is basic, and a very low number, like around maybe like 1 to 3, is very acidic, like strongly acidic, and any number between like 12 and 14 is strongly basic. Okay, so here it's base, and here acid, and here it's neutral. So they're saying suggest the pH of the aqueous calcium hydroxide. So since it's a base, it's a weak base, but it's more than 7 since it's alkaline, so it could be it's more than 7, and then here the pH, and maybe it's equal to 12, so less than or equal to 12, because the weak bases are from around 7 to 12. Here from around 7, greater than 7, and less than or equal to 12. Okay, give the formula of the ion responsible for making solution alkaline. OH minus. Lime water is a saturated solution of calcium hydroxide. Name the gas lime water is used to test for. CO2. We know that when CO2 is in lime water, CO2 turns lime water milky, right? Suggest what is meant by the term saturated solution. A saturated solution is a solution that can dissolve no more solute at a given temperature. Okay, you have to memorize this, okay? So 1 mark for this, and 1 mark for at a given solution, okay? Describe how you would make a sample of lime water starting with solid calcium hydroxide. So first you're gonna get the calcium hydroxide, so CaOH, as a solid, and add it to water, and then you're just gonna filter, and then the filtrate is gonna be the lime water. Filtrate is gonna be the lime water, and the residue is just gonna be the CaOH that didn't dissolve. Okay, so if you wanna make a sample of lime water with solid calcium hydroxide, you're just gonna add calcium hydroxide and water, and then you're gonna filter it using filtration, and then the filtrate is gonna be the lime water, and the residue is gonna be the excess CaOH. Describe how you would test for the presence of Ca ions in a sample of lime water. If you guys remember ZAC, okay, it's Ca, so in NaOH and NH3, it's tick 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 X X and no precipitate. So calcium in NaOH gives a white precipitate, because this whole table is white precipitate that doesn't dissolve in excess. X means it doesn't dissolve in excess, tick means it dissolves in excess, and no precipitate means no precipitate. So again, Ca releases a white precipitate when it's with NaOH that doesn't dissolve in excess, and then NH3 it gives no precipitate. So what do you think we should add to Ca to get a precipitate? We can know it's Ca. NaOH, right? So NaOH, and when you add that we get a white precipitate that does not dissolve in excess. A 25 centimeters cubed sample of lime water is placed in a conical flask. The concentration of CaOH in the lime water is determined by titration with dilute hydrochloric acid, HCl. Name the item of apparatus used to measure the volume of acid in this titration. So if you guys remember when I said like 5 centimeters cubed, 15 centimeters cubed, and 25 centimeters cubed, and 50 centimeters cubed, you can measure all these volumes using a burette. So the answer is burette. Okay, burette. State the type of reaction that will take place. So they're gonna add CaOH, which is a base, and HCl, which is a acid. So when you add these two, you're gonna get a neutral solution. So what is the reaction that's taking place? Neutralization. As well as lime water and dilute hydrochloric acid, state what other type of substance must be added to the conical flask. So in titration, we're gonna keep adding more of the dilute hydrochloric acid until an indicator changes color. So here we have the lime water and we have the hydrochloric acid. The one thing that's missing that they didn't state up here is the indicator, like maybe methyl orange, thymophthalate or phenolphthalein. Okay, so we only need an indicator. That's the one thing they didn't mention. The equation for the reaction is shown. 20 centimeters cubed of 0.05 moles decimeters cubed, so that's the concentration of HCl, reacts with 25 centimeters cubed of CaOH. Determine the concentration of CaOH in grams per decimeters cubed. Use the following steps. Calculate the number of moles in 20.0 centimeters cubed of 0.05 moles per decimeters cubed. So we're gonna use NCV. So if we wanna find the moles, we're gonna do concentration times volume. So 0.05 times 20, and the volume used to be in decimeters cubed, so divide by 1000, and then 0.05 times 20 over 1000. The answer is 1 times 10 to the power of -3, or 0.001. Determine the number of moles of CaOH in 25 centimeters cubed of lime water. So we're gonna use stoichiometry, moles of CaOH to give 1 times 10 to the power of -3 moles of HCl, and then we're gonna write the coefficient of these substances in the chemical reaction. So CaOH, its coefficient is 1, and HCl, its coefficient is 2. So now we're gonna cross multiply, and then x over 1 is equal to 1 times 10 to the power of -3 over 2. Cross multiply, you're gonna get 5 times 10 to the power of -4, or 0.0005. Okay? Calculate the concentration of CaOH in moles per decimeters cubed. So we're gonna use the triangle. We found the moles here, and the volume is given to us over where? Here. So we're gonna do 5 times 10 to the power of -4 over the volume, which is 25 centimeters cubed, and then we divide that by 1000 to turn it into decimeters cubed. So 5 times 10 to the power of -4 divided by 25 over 1000, the answer is 0.02, or you can say 2 times 10 to the power of -2. Determine the concentration of CaOH in grams per decimeters cubed. So there's two ways again. You can either do this number times the volume, so 0.02 times, this number times the molar mass. So 0.02 times the molar mass of CaOH, which is 74, you're gonna get 1.48, or you can find the mass and then divide it by the volume. So 74 times the moles, which is here, times 5 times 10 to the power of -4, mass over the volume, which is 25 divided by 1123. So 74 times 5 times 10 to the power of -4 over 25 divided by 1123. Then you're gonna get 1.48. And that's it for this paper.